Too, you will surely understand. Okay, so today we have module 5, 6th class, your chapter 18 of the book, and what we are doing is serial adder with accumulator. Now you people have seen your adder using parallel binary adder, as well as you had seen in look ahead carry adder. So whatever we do in parallel binary adder or look ahead carry adder is we had seen the logic with 4-bit addition there also. Now we will be seeing the same thing, but we will have a sequential circuit, and we will be having a sequential machine to add this. So let us see what is the addition, as I have been explaining you before also. So as you had seen in this diagram, which you have copied already, you can see I have only one full adder and I have one this delay flip-flop, means data flip-flop or delay flip-flop. You have one delay flip-flop and one full adder, and this is being used again and again. So let me show you what is happening. And of course, when you are using something in sequence, means one by one you are using in sequence, and then other combinational circuit are also involved, like accumulator. Accumulator is something which is called as a series of register kept together which can accumulate a data. Accumulator data means it can keep the data with it till the time told, or till the control circuit says the data should be there with you, it will be there. So that is why the name is called accumulator. So what we see here, you have two registers, one of which is used as accumulator. You will be more familiar with this accumulator word when you do your microelectronics and microprocessor. Okay, so this is 4-bit, this is also 4-bit, and you have a control circuitry here. But what we are saying is we will be doing this 4-bit addition with one full adder and one D flip-flop or delay flip-flop, and all these are being controlled by this control circuit. So what you can see is, when I have only one full adder and we are doing things sequentially, I need to understand what is happening. So what do you understand? When I want to add two number, I will have to add this A naught and B naught, right? So first job of your adder, full adder, will be to add A naught and B naught, and of course A naught and B naught will be added to get S naught. Now this S naught is one bit of the answer. This S naught is one bit of the answer. We need to keep it safe, and after I get S naught, I do not further need this A naught and B naught. Once this S naught is created and once your C naught is created, A naught and B naught can be we do not need any further A naught and B naught, and it can be deleted from my system. I do not need it. After this addition, next what I want A1, B1 to be added. So the same full adder will be fed with A1 and B1, and also it should be fed with C naught. So I need to see in my machine that A1, B1 and C naught is present together to the full adder. So my job is to give full adder A1, B1 and C naught at the same time, because full adder is a combinational circuit, and a combinational circuit act immediately when it has all its input. So that is why it is called as combinational circuit, because it combine all the input in certain form and give you the output. So A1, B1 and C naught should be presented to the your full adder to give you the next combinational operation. So when it gives you next combinational operation, it will give you S1 in the answer. You know that full adder has two output, that is sum and carry. So when you are giving C naught, A1 and B1 to full adder, it will present you S1 and C1. Now you need to keep this S1 safe somewhere, because this is again your part of the answer, and this C1 should be holded for one clock cycle so that it is available for next clock cycle along with A2 and B2. along with A2 and B2. So this C1 along with A2 and B2 will be presented again to the full adder. So same full adder is doing the job. T0 time it is adding this, T1 time it is adding this, T2 time it is adding this. So at T2 time your C1 should be available, and when your C1 is available, by that time you do not need this A1 and B1. Let it get vanished from the system. You do not need it. So this goes on for another 2 cycles of T2 and T3. It goes on, and again it will add, your full adder will be adding your, the fourth operation it will be doing of adding A3, B3 and C2. Now S3 again need to be saved, and the carry here should also be available now for my answer. So my answer is this. So what did you understand? We understood that we need a full adder which can add 2-bit or 3-bit whatever at a time. You need to keep your S0 to C3 safe. Your B0 to B3 and A0 to A3 can be lost after doing the operation. Now I want you to see the circuit. You have understood this. So what you see now here, your X0, X1, X2, X3, you can take it as your A0, A1, A2, A3, and Y0, Y1, Y2, Y3 can be taken as B0, B1, B2, B3. Now what happens? You have this control circuit. And what does this control circuit do? This control circuit will have, it will have a clock output, which will, because everything is governed by clock, no? I told you T0, T1, T2, T3. When I have these 4 time clock cycle, my operations will be done as per the clock only. So now what happens at time T0? See, we understand. Then first is your this start signal. When it says start, means the circuit is on. The circuit is on means as soon the circuit is on, we have to assume that your X and Y are loaded also. So that is why I am telling that at T0 time, the first bit addition happens. At T0 time, first bit addition happens. So when start signal is given high in the control circuit, as soon as the start is high, your these data of Y and X are loaded in this circuit. This is called as accumulator and this is called as addend register. Now what happens at T equal to T0, Xi is equal to X0, Yi is equal to Y0, and when you have your start signal high, you will have your Ci as 0. So your first bit addition happens. Now first bit addition means, I think okay, so your first bit addition means your A0 and B0 are getting added here. Now what did I tell you? I told that this S0 need to be saved because this is part of my answer. Where is this S0? This S0 is here. Now what you can see, this S0 is going back and getting here, and SI means serial input. So you people note it down. SI means serial input. So this S0 goes here, and with this serial input, it goes and sits at this place. Now, when you get your S0 here with serial input, it will go and sit on X3 only. Why? Because it is a 4-bit register only. So what you need, along with this serial input, you need to shift your data. I told you what? As soon as I get my S0, my A0 and B0 is no more needed. So what happens? When your S0 comes, the data shifts to right by 1 bit. So you will have your X3 here, X2 here, and X1 here. Same way, you will have your Y3 here, Y2 here, and Y1 here. Why? Because my X naught and Y naught has given its job of addition. Now, because the data is shifted to right by 1 bit, your X3 is vacant now, and X3 has a space to keep your S naught through the serial input, which have been added at T naught time, which have been added at T naught time. At T naught time, this addition happens. So what happens at T1 then? And you can see here your S naught is going with the feedback to serial input and sitting at X3 place. And what is happening to this C naught? C naught has come here. See, I plus 1 is C naught as of now. What is happening? It goes to D flip flop. And this D flip flop is enabled as soon as you can see this CE. CE is what? CE is chip enable. And let us see from where the CE is coming. CE is coming from the same shift output signal. SH is shift. You can see SH control, shift control is given by this control circuit to this shift, and also it is going to D flip flop to chip enable. That means what? With your shift control signal, the bits in the accumulator shifts, the bits in the addend register shift, and also your D flip flop is enabled. So what happens at the with the same control input signal of shift, place is created for S naught, and your D flip flop is activated to store your C carry output C naught to store in the D flip flop until further use. And what is the further use? Further use comes at T1. Further use comes at T1. And what happens now? When the data is shifted, at this place you have your X1. At this place you have your Y1. And in this place you have your C naught. Can you see? T1 time has come and my circuit is ready to add X1, Y1 and C naught. At time T1, full adder will add these 3 bits and you will get your S1 here and you will get your C1 here. Now what will happen? Before you put your data, serial input data, before you put that data, what will happen? Your shifting will also happen. So shifting will make your, here you had your S naught and now here you will get your, here you will get your S1, right? So what will happen now? Here you will get your S1. Okay, I will explain with the other thing only. Okay, so what do you get here? Here you get your S1 at the 4th bit place and here you get your S naught. And because why I need this? Because A1 and B1 is no more required. A1, B1 means your X1, Y1. X1, Y1 is no more required. So what you will get here? You will get your S naught, S1, and here you will have your X3 and X2. So this operation keeps on happening for 4-bit time. And finally what happens? Your 4-bit of data, that means your S3, S2, S1 and S0, where it will be? Here, S3, S2, S1 and S0. And where will be your C3 available? C3 will be there as stored in this D flip-flop. And somebody can tell me what will happen in addend register? What data will be available in addend register after this 4 clock cycle of T0, T1, T2, T3? Can you think and tell me? At T2, this added. At T3, this added. At T4 time, I will have C3 in D flip-flop and S3, S2, S1 and S0 in accumulator register. Can somebody tell me, seeing the circuit, what will be there in addend register after this 4 clock cycle of T0, T1, T2, T3? What will be there in the addend register? Accumulator, your answer is there. S3, S2, S1, S0. And C3 here in D flip-flop. What will happen in the addend register? What you will get? Can you see here also you have a feedback here. So the data, your B input, your second addend input, it will be cycling here, and after 4 clock cycle there will be shifting of the data. Y3 will come here, then here, then here, then it will go back and sit here. So after 4 clock cycle, addend register will have same Y3, Y2, Y1, Y0, but accumulator will have S3, S2, S1, S0, and your C3 will be available here. Now whatever I told you now, you should understand that in form of state diagram also. Now state diagram means, see, this is what whatever I told is being shown. At time T0, what is happening? Your data is like this. Control input has done all this, and your full adder is adding Y0 and X0, and C0 is 0 at initial phase, and you get your S0 and C1. At time T1, what is happening? Your S0 and Y0 is sitting here. Why Y0 is sitting here? Because Y0 is fed back here. So Y0 comes here, and Y3, Y2, Y1 get shifted here. And at full adder, what will be available? Your X1, Y1, and this C1, whatever is going to D flip-flop, is being stored there for further use in the next clock cycle. So at T1 this happens, T2, T3 and T4. Now it is not being used because your data is here. So as I told you, S3, S2, S1, S0 is here, and C4 is here. So your complete data is available here. And what do you have in your second register? In your second register, the same data will appear after moving one circular shift. Okay, so this is your operation. Now what I was asking you was that you should understand this state graph. Now what this does, this state graph says? State graph says it will have 4 state, S0, S1, S2, S3. At S0, it will remain at S0 till your start is high. If start signal, ST start, if start signal is 0, it will remain in S0 and no shifting will happen. But as soon as start signal become high, it will grow from S0 to S1 when start signal is high, and also shifting will happen. So this state graph is only talking about the shifting operation. Adding and all is happening using combinational circuit. We need not bother about that. But what is the role of your control circuit? Your role of the control circuit is to control the sequential part of the circuit. Sequential part means what? It has to shift, it has to go to next state, and all that is the operation of the control operation of the sequential machine. Your combinational circuit, adding will do its job, your D flip-flop will do its job. So this is only about the control circuit. So what you see, when start is 0, S0 remains as S0. But when start becomes 1, S0 changes to S1 and shift output is given. Shift output will do what? You know already. It will shift the bit of the register. And same thing is happening again and again at S1 to S2, S2 to S3, and S3 to S4, S0. So what you can see here, when it is at S1, after that it goes to S2, and your start signal, because it is a dash here, for rest of the 3 state change, dash means what? It will work for both 0 and 1. So it becomes a don't care. Start signal becomes don't care after it reaches state S1. So what happens? It goes to S2, S3, and finally to S0. So this is the state graph of serial adder control. Now when you get a state graph, you know what next has to be done. Next you will denote the Boolean variable to it. So S0 will be 0, 0, S1 will be 0, 1, S2 may be 1, 0, and S3 may be 1, 1. After that, what do? You can simply bring it in this form. You know this, right? S0 to whether your start is 0 or 1, it is going to S1. Then it is going to S3. Then it is going to S0. This is your simple state transition table in the form of Boolean variable. You know this. And then what do? You get your DA, DB, and shift. Shift signal K maps. Now, what do you see? What all is happening? You know that shift, where shift is coming? Shift is coming to the, it is going to both the shift register, right? It is going both to the shift register. And in total, one more thing you have to understand here is, see here, one more thing. This is a state graph of n bit circuit. You saw state graph of 4-bit. What if I have a n-bit addition? N-bit addition, how it is done? You can see here, S0 to S1, no change. S1 to S2, no change. But from S2 to Sn minus 1, you can see a dotted line here. And this dotted line says what? Till it reaches the last but one state, it will keep on shifting. Can you see here? It keeps on shifting. When it reaches the second last state, for the final state change, it goes to S0 with the last shift. So you can see this dotted line, and this is for n-bit addition. N-bit addition. Because they can't keep on doing S3, S4, S5, S6, and so on. So they have shown S2 to Sn minus 1. Now the next state graph, what does it show? It shows that it is adding one more state of stop. One more state of stop. And what they want to show here that start signal will become 1 for first bit addition, that is your X0 and Y0, and it will become 1 again for the last stop bit. And when the last bit comes and it stops, after that it will go to the initial state of S0 by making start bit again 0. So this state graph has addition of one more state, that is stop. And this is one variation which is shown here. Things are all possible without this stop also. Okay, so this is all about your state graph and serial adder with accumulator. If you have any doubt with respect to your circuit and all, you should ask me.